Hexane is a straight-chain alkane made up of 6 carbon atoms. It is a highly versatile and widely used organic solvent that finds application in numerous industrial processes. Hexane's unique combination of properties has made it a popular choice for tasks such as oil extraction, cleaning, and a variety of chemical reactions. However, despite its usefulness, hexane has also come under increasing scrutiny due to its potential health effects and environmental concerns. As awareness grows, industries are beginning to seek safer alternatives. This article delves into the characteristics of hexane, its historical and industrial significance, associated health and environmental concerns, and emerging alternatives that could eventually replace it. The history of hexane can be traced back to the mid-19th century. It was first isolated in the year 1849 during the distillation of crude oil. At that time, the petroleum industry was still in its infancy, and many compounds derived from oil were being studied and catalogued. Hexane soon caught the attention of chemists for its impressive solvent properties. As petroleum refining technology advanced and became more widespread, hexane became more accessible and began to see broader use. By the early 20th century, hexane was already a staple in several industrial applications. During the mid-20th century, the growth of the food and chemical industries significantly expanded the use of hexane. It became especially prevalent in the food sector, where it was employed to extract edible oils from seeds and nuts. This was largely due to its efficiency and cost-effectiveness. Compared to mechanical pressing, hexane extraction offered higher yields and more consistent results. By the 1960s, hexane had cemented its place in industrial operations, including tasks like degreasing and heavy-duty cleaning. As concerns about environmental preservation and occupational safety grew in the latter half of the 20th century, regulatory bodies began to evaluate the safety of hexane more closely. Agencies such as the Occupational Safety and Health Administration and the Environmental Protection Agency introduced measures to monitor and limit hexane exposure in workplaces. These regulations signaled a shift in how solvents were perceived, and many industries began implementing more rigorous safety standards as a result. Hexane is a saturated hydrocarbon belonging to the alkane family. Its molecular structure consists of a straight chain of 6 carbon atoms, with hydrogen atoms filling all available bonds. This structure gives hexane its nonpolar nature, which is a key reason for its effectiveness as a solvent. In addition to its primary structure, hexane exists in several isomeric forms. These isomers include N-hexane, 2-methylpentane, 3-methylpentane, 2,2-dimethylbutane, and 2,3-dimethylbutane. Each of these isomers has slightly different properties, such as boiling points and volatility levels, making them suitable for different applications. The physical properties of hexane contribute greatly to its utility. It has a boiling point of around 68.7 degrees Celsius, which allows it to evaporate quickly. This is useful in applications where fast drying is required, such as in paint and coatings. Hexane's density is lower than that of water, which means it will float, an important characteristic in many separation processes. Being nonpolar, it is excellent at dissolving other nonpolar substances, such as oils and fats. This solubility characteristic underpins its role in the extraction of vegetable oils. From a chemical standpoint, hexane is relatively stable. It does not react easily with most substances under normal conditions, which adds to its desirability as a solvent. However, it can combust in the presence of oxygen, releasing carbon dioxide and water while generating heat. This property makes it a viable component in certain fuel mixtures. Among its most prominent applications is oil extraction. The process involves several steps, starting with crushing and heating seeds or nuts to release oil. Hexane is then mixed with the crushed material, where it dissolves the oil to form a hexane oil solution. This solution is subsequently filtered to remove solid residues. In the final step, the hexane is evaporated from the oil using a distillation process, allowing for its recovery and reuse. This method is favored over mechanical pressing due to its ability to extract more oil. In fact, the majority of vegetable oils produced in the United States rely on hexane extraction. In the chemical manufacturing sector, hexane is used in the production of substances like rubber, coatings, and adhesives. Its solvent properties make it ideal for dissolving and mixing various ingredients to achieve desired formulations. For example, hexane is commonly used in the creation of acrylic resins. These resins are valued for their clarity, durability, and adhesive properties. In rubber production, hexane facilitates the blending of components, ensuring uniformity and performance. Hexane also finds application in industrial cleaning and degreasing. Its ability to break down oils and greases makes it a preferred choice for cleaning machinery and mechanical parts. Industries such as automotive manufacturing use hexane-based cleaning agents for maintenance and preparation of equipment. Additionally, hexane is used in laboratories for various extraction procedures and chromatography techniques. It is especially common in thin-layer chromatography, where it helps to separate compounds based on their polarity. The fuel industry also benefits from the properties of hexane. It is often blended with other hydrocarbons to enhance the performance of gasoline. Hexane's high energy content contributes to the efficiency of fuels used in transportation. It can help improve engine performance while reducing the amount of harmful emissions. Despite these benefits, hexane poses several health risks, particularly with prolonged exposure. Individuals working in environments where hexane is used extensively may be at risk of exposure through inhalation, skin contact, or ingestion. One of the most serious concerns is its potential to cause neurological damage. Chronic exposure to hexane has been linked to peripheral neuropathy, a condition characterized by numbness, tingling sensations, and muscle weakness. Research conducted in the 1980s highlighted the link between hexane exposure and neurological symptoms among workers in the shoe manufacturing industry. Inhalation of hexane vapors can also lead to respiratory issues, such as coughing, wheezing, and shortness of breath. Long-term exposure may contribute to the development of chronic respiratory conditions. To mitigate these risks, organizations like the American Conference of Governmental Industrial Hygienists have established threshold limits for hexane exposure. There is also concern about the potential reproductive and developmental effects of hexane. Some studies suggest that exposure could impair fertility and affect fetal development. While ongoing research aims to clarify these risks, agencies like the National Toxicology Program have already classified hexane as a possible reproductive toxin. To reduce exposure risks, workplaces are encouraged to implement safety measures, including the use of personal protective equipment, adequate ventilation, and routine air quality monitoring. Beyond health risks, hexane poses environmental challenges. As a volatile organic compound, it contributes to air pollution when released into the atmosphere. It can participate in reactions that lead to the formation of ground-level ozone, which has harmful effects on both human health and the environment. Moreover, hexane can contaminate water bodies through improper disposal or accidental spills. It does not dissolve easily in water, which means it can persist in aquatic ecosystems and pose threats to marine life. Soil contamination is another concern. Hexane spills can degrade soil quality and affect plant growth. Over time, this contamination can also enter the food chain, potentially impacting human health. Cleanup and remediation efforts are often costly and complex. To address these issues, environmental agencies have put regulations in place to control emissions and manage hexane waste. The goal is to encourage industries to adopt more environmentally friendly practices. In light of these concerns, several alternatives to hexane have emerged. Ethanol, a renewable solvent, is one such option. It can effectively extract oils and fats from plant materials and has a more favorable environmental profile. Ethanol extraction processes have been shown to yield oil quantities comparable to those obtained using hexane. Supercritical carbon dioxide is another promising alternative. This method involves using carbon dioxide in a supercritical state to perform extractions. It is non-toxic, environmentally benign, and leaves no harmful residues. Furthermore, the extraction parameters can be adjusted to selectively extract specific compounds, enhancing efficiency and product quality. Cold pressing offers a completely solvent-free alternative. Although this method typically results in lower yields, it preserves the natural flavor and nutrients of oils, making it attractive to health-conscious consumers. Cold-pressed oils are becoming increasingly popular in the food market, The development of green solvents derived from renewable sources is also gaining momentum. For example, limonene, extracted from citrus peels, is used in cleaning products and has a lower environmental impact. Acetic acid, commonly used as a solvent and preservative, is another biodegradable option with a relatively safe profile. Industries are gradually transitioning to these alternatives, driven by stricter regulations and consumer demand for sustainability. Food manufacturers, in particular, are beginning to adopt ethanol and supercritical carbon dioxide methods for oil extraction. These alternatives not only improve worker safety but also align with goals for environmental stewardship. Looking ahead, the future of solvent technology is promising. Innovations such as ultrasonic and microwave-assisted extraction are being explored as more efficient and safer alternatives to traditional methods. These techniques offer advantages like reduced energy consumption and faster processing times.